So thanks again, everyone, for your time today. And I'm going to talk to you today about something we're calling SPEED-CHROM at Corteva, and walk you through the journey we've been on over the past year and 9 months or so on this. And also wanted to send a particular thanks to Jen, the previous presenter there, for the in-depth kind of technical discussion on automated method development and the theory behind it, because my talk is very complementary to that in that it's very pragmatic. So thank you for laying that foundation. It's going to set us well if you listen to that talk on what we're going to talk through today. So a little bit of background to get us started. For those of you unfamiliar about Corteva and who we are the agricultural division of DowDuPont and their merger that happened in 2019. So if you aren't familiar with our name, you will almost certainly know these names of Dow and DuPont and the rich heritage that we have. And this is going to come up a couple times in my talk about this heritage and the journey we've been on since 2019 at Corteva and establishing ourselves as a company and the problems and challenges that we faced as a part of this. And also, wanted to give a little context on the need for sustainable crop protection. So obviously, all of us know the importance of food and eating and nutrition, and that's really the journey and what we provide at Corteva, providing solutions for our farmers to grow more food more sustainably. So a couple of things here, obviously we're all aware of climate change and the impact that's happening in the world and on our environment, putting stress on our agricultural system and the ability to grow more food. Additionally, the population of the world is increasing, so we need to grow more food. And something that isn't covered here, but is important, is the amount of arable land that we're using for agriculture is certainly decreasing across the globe. And so what that really adds up to is we need to grow more food with less. With less land, less water, less resources. So that's where crop protection really comes in and helping our farmers provide that solution for the world. So we're really focused on developing technologies to help farmers sustainably increase production of healthy food and minimize the environmental impact. So there was actually a really good poll question yesterday, if you were in the session, about where you sit in your organization, and the majority of people were actually in discovery. And so to kind of start us out here, I wanted to give some context on where I sit in Corteva, so you have a little bit deeper understanding of where I'm coming from in the presentation. So I sit in that pre-dev and development part of the pipeline, helping our process chemists develop the chemistry, develop the process, and deliver material for our field trials across the globe so that we can understand and provide those solutions to our farmers. And certainly, a lot of people from pharma, I'm sure, certainly our presenters were, and I would imagine a lot of people familiar with that. None of us are strangers to the amount of time and money that it costs to come up with a new molecule and bring it to market. So in the ag space, we're looking at about 10 years and $250 million to bring those to market. So a lot of time, a lot of money, and doing more with less, just like our farmers is an important part of the aspect that we're working towards and driving towards at Corteva. So the ARDT separation scientist, that's my group. You can imagine, and I'm sure all of you feel this too, as analytical chemists, that we wear a lot of hats. We have to develop our methods. We need to transfer them a lot of times to people that might not be trained or have as thorough of a training as we are. For instance, in my work, such as our process chemists, they're not trained analytical chemists. They're trained process chemists trying to do that. Redevelopment as our route changes and analog changes, we find something new, an impurity in the chemistry. So we're constantly iterating to improve our methods, and all the while trying to maintain our documentation for our project groups and those who come after us. And with all these hats that we wear, at least at Corteva, we're never working on one project, right? We always have multiple projects and timelines that we're trying to meet, which really drives us to where we're trying to get to with our goals for SPEED-CHROM, which is increase experience in the group is our first goal. And this really does feed back into that first slide of who we are as Corteva, and that spin-off in 2019 from Dow DuPont. And we need to, we used to use the phrase, we're a 200-year-old startup. And although that's kind of cheeky, I really do think it's indicative of where we are in the journey we've been on. We're pretty young as an organization, and we definitely need to increase the experience in our group. So that's our first goal for SPEED-CHROM that we set off to solve. And our second goal, I'm sure everyone in every role feels this pressure from their leadership, their management, and that is to increase productivity. We're always trying to go faster. We're trying to be more thorough. We have our pressure from our regulating bodies to provide more data and improved quality data for our studies and our molecules. And so we really do need to drive this increase in productivity to deliver upon the solutions that our farmers and consumers need. So these are the goals. I'm gonna give my talk through the lens through which I'm viewing it, and hopefully by the end of the talk today, you're able to gather that we've achieved these. So what is SPEED-CHROM? So first and foremost, I do work in a corporate setting, and you can't have a corporate initiative without an acronym. So SPEED-CHROM is an acronym for Software Assisted Process for Efficient and Expedited Development of Chromatographic Methods, which is a mouthful, which is why obviously we just go with SPEED-CHROM. But at the end of the day, it's a workflow for HPLC method development to improve the speed and productivity. Where this is centered around ACD's method development suite, and we're going to talk about that here today. So the first question that might come to mind is what's different from previous approaches? And depending on your industry and where you sit in your pipeline, I would imagine there's a few different approaches that people on this call might take, or the way their organization might be structured. So traditionally at Corteva, we were focused and structured on molecule or project. So we're gonna talk through the dedicated analysts that we had, a little bit shift in that gear for us. The instrumentation and the software that we're using, those are kind of unique and special. But I would like to spend the majority of my time today talking about the strategy that we're employing in our workflow. So dedicated analysts, as I alluded to on the previous slide, we traditionally at Corteva have aligned by project or portfolio. So this is our first attempt in our analytical division to align to a technology. So we dedicated analysts that we could train up and focus on the workflow and the process to really output our methods quicker. Train them on the software, train them on the instrumentation and the strategy we're implementing, so that we can employ those tools more efficiently and faster. One of the challenges that at least we faced at Corteva is, when working through the software and the tools, there is a lot to learn. You have to learn the fundamentals of chromatography. At least for us, we do everything mass spec guided. So you need to have some background in mass spec. You need to know the workflow, and then also the business aspect of, kind of the previous talk, where you need to know the end use of your method to be successful in your method development. So these are all challenges that we faced, and this is the approach that we took to solve it by dedicating analysts to this workflow. So the second is the instrumentation, and I'm not going to go too in depth here, but I did want to highlight a few things that are unique. So the first is the pump and solvent system that we use. So in our HPLC for method development, we use a quad pump, and this gives us the flexibility to combine different pHs with different strong eluents for really rapid method development. So on our A channel, we have a 12 solvent selection valve, so we can have different aqueous buffers, and B, C, and D can be different organic solvents to rapidly iterate and screen different conditions to get methods faster. The second is our column compartment. So shown here is we have an 8-position valve in our column compartment, and we have to dedicate one of those as a bypass. So we have 7 columns in total. And I don't have the specific columns we use on our system listed here, but I did find a reference here from Ahmed et al. that shows a very, very similar approach to what we're taking, based upon the hydrophobic subtraction model. For different buckets of different columns, we choose a diverse set of columns in our screening system to give us the best chance of success at finding something that works. And then we kind of have a catch-all bucket as well of different or unique stationary phases that can be screened if needed. And we'll talk about this in the workflow in the coming slides. And then the third is the detectors. We keep it relatively simple. Our focus and my role is a separation subject matter expert is chromatographic method development. So we're not necessarily focused on high-res MS or structural elucidation in my specific role, but it does feed into, we work very closely. My cube mate is the structural elucidation expert on our project, and we work very closely together. So it all works together to provide quality methods to enable that work. So we use the DAD and the MSD on our system. So the software, obviously, we're here with ACD talking about this, and it's a critical part of our workflow. There's just a couple of things I wanted to highlight. We're not going to go in depth on the software today, but the big ones for me are it helps organize our data. You can imagine with different columns, mobile phases, analogs, projects, you can generate an incredible amount of data really, really fast. And that's really important in our current state of technology to iterate and deliver solutions faster, but you need a way to keep that data organized. And ACD is definitely really, really phenomenal. Specifically, what we use for that is AutoChrome in accomplishing that. Secondly, it controls the instrument. I'm sure all of us have had these times where you sit down, you try and run some conditions, maybe you program your equilibration step wrong in your gradient, or you put the wrong column position or the wrong mobile phase position. It just sets you back. So by having that integrated control of the instrument, it allows you first off to design your experiments very quickly and also control them and eliminate that human error on that instrument control as well. So huge, huge advantage there using AutoChrome. And then finally, again, this has been talked about in previous talks, that we can model conditions based on empirical data. And this is really, really important for us. We need to be able to get real data on our real analogs and then make decisions off of that data. So it not only enables us to collect more data, but it makes the data that we're collecting more powerful. So these are really, to me, the key features of the software that we're utilizing here. And then finally, the strategy. Again, I wanted to spend probably the majority of our time here today talking about this. So here is our overall workflow. And if you can't read this, don't worry, that's on purpose. And we're just going to go through the main points of the workflow that we've employed at Corteva to implement these tools successfully into our workflow for SPEED-CHROM. So the first step we want to focus on is we want to model what we can to get the right data. Corteva, in my role, we're almost exclusively focused on small molecules. So keep that in mind too, in our workflow and the context of what we're discussing today. But one advantage that we have for small molecules is that through tools like ACD's PhysChem history, we can really accurately predict pKa's. With that prediction, we can upfront, before we even run anything, in 5 minutes, make a determination on where we might need to be in our pH space for our mobile phase. So that's shown here on the log D versus pH, and then our charge state versus pH graphs. These are an example from the PhysChem history. So we can put our structure in there, we can predict what the charge state's gonna be at different pHs, and then determine if it's gonna be charged or not. Again, we basic chromatography, we want to target a space in general where our analytes, or as many of our analytes as possible, are not charged. We want to target that ion suppression range. So we can predict that, see where we are. We also target to produce mass spec friendly methods in our chromatographic group so that we can easily transfer them to our structural elucidation colleagues or different research labs around the world. So we will always start in that acidic pH range with 0.1% formic acid, and then we're going to go from there. So this is really, really powerful. Although most of our molecules honestly don't end up being charged, the ability to predict it is just too powerful and too easy to not use at the front of our workflow. So we'll predict it, make a decision on what pH range we want to operate in, and then move on to the next step in our workflow, which is going to be column screening. So, we'll do our column screening, either it's acidic or a targeted pH based on the prediction, and make a determination on that. So a couple of things I wanted to highlight here. We already talked through the hydrophobic subtraction model briefly, and how we're employing that, but suffice it to say, we want to target diverse column chemistries. And this graph on the right side of my screen is kind of showing some historical data for in our laboratory for different columns in the number of methods on the y-axis that were produced. And this is color-coded, and I apologize if it's a little hard to see, normalized to the acinus, the column 1 there. So we're targeting a primary C18 for method development, and then these darker blues, column 2, 3, and 4, are considered functionally similar. Those are FS score less than 3 using the hydrophobic subtraction model. So those are considered equivalent columns through that theory. And then the middle columns 5 to 18, the slightly darker blue, there are kind of this gray area of, they're a little bit different, but not necessarily considered orthogonal columns to our standard C18. And then the darkest blue way on the right, columns 19 to 22, are considered orthogonal columns to our standard C18. And why this is important, or the takeaway we kind of took from this, is we're actually not using it maybe a super diverse set of columns historically in our method development. And so what that enabled us to do is two things. One is maybe simplify some of the columns here and remove them from our screening protocol so that we don't need to run them every time and increase that speed, that turnaround. And two, provide that data to our analysts who are using the workflow to not get hung up on this. I've historically seen a lot of people get hung up on column screening and spend a lot of time, particularly early on in method development, with a new analog or a new molecule that maybe you're not super familiar with. And so we're providing this information to our analysts to say, hey, this isn't something that, at least the beginning, you need to spend a lot of time on. Make a decision quickly, move on, and get a fit for purpose method into the hands of our stakeholders. So we talked about the pKa, the column screening, and then the final one is our mobile phase screening. So this is the workflow we chose, and this was a balance of turnaround time and throughput. So obviously, mobile phase screening is incredibly powerful. This can be done in combination with the column screen, but for the purposes of our workflow, this is just the order of operations we chose based on the percentage of the historical methods that use different approaches. But I will say that what's really nice about the mobile phase screen, particularly using the ACD method development suite that we're employing, is this can also be modeled based on empirical data using a single mobile phase or a combination of mobile phases, and obviously combined with the instrumentation that we discussed earlier, you can iterate through those very, very rapidly. So this is a huge advantage, and this was kind of a strategic decision just to get the target turnaround time that we were targeting for our process. And finally, on the strategy portion is going to be, getting the information we need to process the request. For our workflow, we targeted a Power App and built a request portal through Power Apps just in Microsoft. And the reason we did that is it's something that we have complete control over. It's fairly easy. We can do that ourselves. We don't have to leverage any IT resources to do that. And our main goal in doing this was to gather the needed information up front. You can imagine we sat down, talked through, and strategically aligned to what information is needed for chromatographic method development, the requester information, the types of samples that are submitted, diluent structures, so we can do our predictions. We're collecting that and aggregating it all up front and organizing it in our request system. And that enables our analysts to spend more time on method development and not trying to track down this information from the requesters. And then the final piece here was we automated our notifications and file structure as much as I can. So the moment a request is submitted, a folder is made that all the data can go into, and then we use a Kanban board type style workflow in the Power App that enables us to go from submitted to in process, align it to the analyst, and then also to completed. And the requester gets automated notifications all along the way, including the results. So that really, really is a huge time saving that allows our analysts to focus on science and not necessarily on the communication, because we've gone through the effort to automate that as much as we can. So hopefully you see the whole workflow here. Kind of at the end of this, after we work through those, is we'll screen and select internal standards, document the work that was done, and our initial method development is complete. So the highlights there again are we're going to model what we can, the PKA prediction, automate our screening using the software and the tools, and enable quick decisions through the theoretical and historical data for our analysts to really move quickly and iterate on those methods, and give our teams the power to make informed decisions quickly. We really, again, want to empower our employees, especially as they're learning, to do this. So now I wanted to go through just a couple really quick examples of how this works on some real molecules we've seen over the past year. So request comes in, and this was a route scoping project. So you can imagine, being in process development, we do a lot of this, and depending on what stage or phase of the molecule's life cycle it is, the chance of these going forward is usually relatively small. So we want to efficiently deploy our resources in our analytical chemistry department to focus on the hard problems and not the ones that are early on or proof of concept type stuff. So this is certainly something that fell into a proof of concept type scenario, and we want to get a method that we know works and follows our best practices into the hands of our process chemists as quickly as possible, so that they can show the proof of concept and whether it works or not, and then make a decision on how to move forward, and them not be waiting on us for data. So we're going to predict our pKa. This is a scenario where it was neutral at that lower pH range in the acidic pH range, so nothing unique or different that needed to be done there. We're going to screen our columns. The chromatogram is small down there, but the short and sweet of this is one that we didn't see large selectivity differences based on column, at least not for the impurities and the analyte of interest that we're targeting here. So we're just gonna, again, using that historical information, make a decision quickly to our primary C18, and then we're gonna do our gradient optimization. And actually, this is a case where everything's separated without really any strong effort. This worked really quickly, and we're able to report this out to our process chemist. So really, this really was a quick win of a one-day turnaround. The method's fit for purpose. The process chemists can get the data that they need, and also, I'm sure all of you can appreciate this. It follows our best practices for columns, mobile phases, and internal standards. It can't be understated. I'm sure I think the historical saying is always, what's the best column? The one that's on your instrument. But we really want to get away from that, be strategic, so that we can increase the likelihood of our stakeholders having the columns, our CROs, and then also in the global world that we live in, we have labs all around the world, in India, China, Brazil, France, here in the US. So we want to ensure a robust supply and pipeline, because that's also been an issue on our projects in the past, that we have columns available to transfer to our labs regionally and to our CROs around the world. So this is really a quick win, an example from some work we've done recently. So here's another example. This is an enzymatic catalysis route scoping that was being done. And this was a little bit earlier stage project. And so again, we're gonna predict our pKa, and this is actually an example where you can see that line there at 8.3, where we actually do need to target a specific pH range to suppress the ionization of this molecule. So we're gonna do that in our screening. Because we're above a pH of 8, we're gonna target columns that are stable, are known, should be stable at that pH. Obviously, silica, we all know is gonna degrade over time, the more alkaline and pH that you get. So we're gonna target at the beginning columns that are gonna be more suitable to those conditions. And then we're gonna do our optimization for the chemistry. So this is a little bit different example, but again, that prediction up front really enables you to get the right data on the columns in the MOA phase and get this out the door quickly. So this one took a little bit more time. This one was a 6-day turnaround, mainly because we're working on training some people. But again, I think 6 days for most workflows is really, really good. And this actually gives us a little bit more in-depth information that this one was one that actually needed a specialty detector, ELSD or MS. So that's a conversation we can have with our process team on if they have that equipment available, or do we need to target a different technique for the method. And actually, based on this data, we did prioritize GC, but we got that data really, really quickly. We didn't waste a lot of time and effort on it, and we're able to iterate then to the GC. So that's just as important, right? Those false negatives or that informed decision making. Although this wasn't the method that was employed, getting that information to the team as quickly as possible so they can progress with their research is really, really important. So to round us out here, I wanted to bring back the goals that we set out with of increasing experience in the group and increasing productivity. So how have we done on those? We're almost to the end of the year. It's performance season, I'm sure, for me and a lot of you. So where are we at? We had a target of 75 methods through SPEED-CHROM this year, and we're just a tad underneath that, on a running average. So we're just behind, but I think this is a great success. That was targeted due to the throughput needed in our laboratory. Obviously, depending on your workflow and where you sit, that may differ. And this would be a huge efficiency gain for our lab and the amount of people that we have working on this. So although not quite at the target, this was an ambitious target we set out with, and we made really good progress on this year. And the second is the turnaround time. This is actually a new metric for us. I don't have historical data to compare against here, but we're targeting a turnaround time of 5 days, a work week, to get results in the hands of our stakeholders and our process chemists. And we're so close to achieving that, and I really firmly believe we're going to be there by the end of the year. So by doing this, we have increased the efficiency for sure. We've decreased, well, I can't say for certain we've decreased our turnaround time, but certainly we're measuring that and can provide that data to our stakeholders. And by increasing the productivity, we're able to put our newer employees, our younger employees in the SPEED-CHROM team, get them this in-depth exposure and experience as quickly as possible so that they can become true experts in chromatography and contribute to their project teams as quickly as possible. So in summary, a robust workflow, for reverse phase method development, and enables our new team members to onboard quickly and gain experience, frees up the times to work on challenging and difficult tests or technology development. And obviously, we're always looking to improve our workflow, so we'll be continuing to work on that in the days and years. Everything always takes a village. So these are all the team members that contributed in some way, shape, or form to this. And the ones in blue on the right are my process colleagues. And without further ado, I'll take any questions you might have. Thank you.